Okay, welcome back dear students to the tutorial about the chemical applications of group theory. And this is the fifth video in this series. We are discussing the application of group theory in spectroscopy. Okay, in the last video we had discussed that the more IR and Raman active vibrations, that is which vibrations are IR active and which vibrations are Raman active, and we have studied that only those modes in which their symmetry belongs to x, y, z Cartesian coordinate are IR active, and the modes which belongs to the linear combinations of x, y, z, that is x square, y square, z square, are Raman active. Okay, and now in this video, we are going to discuss about the complementary character of IR and Raman spectra. Okay, that is mutual exclusion principle. And we have studied, I think you might have studied in your UG level that in the case of center of symmetric molecules having center of symmetry, the Raman active vibrations are never be IR active, and IR active vibrations cannot be Raman active. That is the case of centrosymmetric molecule, and that is called a mutual exclusion principle. And in this video, we are going to explain this mutual exclusion principle using the principles of group theory. Okay, listen carefully. Okay, consider molecules having centrosymmetry. For example, molecules like C2H4, molecules having C2H4 having the point group D2H, okay, and molecules like S sub 6 having point group OH. These are centrosymmetric molecule. Centrosymmetric molecule, we know that there is a element called the center of inversion. I will be there in the case of centrosymmetric molecule. Center of inversion will be there. Okay. So if we operate this I operation, center of inversion, on XYZ coordinate. Okay. In the case of centrosymmetric molecule, there is an inversion center, symmetry element called the inversion center, I. So during the operation of I, XYZ coordinate, we know that changes sign, that become negative. Okay, so the character of I will be -1. Character of I will be -1. Hence, all representation generated by x by z, all representation generated by x by z, the character of I will be -1. So that representation is denoted as U. Okay, I think you may remember that in the case of Mulliken symbol, we have studied that in the case if character of I is equal to -1, that is denoted as U. Okay, like B2U or A1U, like that. Okay, that is ungrayed symmetry. U means ungrayed symmetry. Okay, so XYZ coordinate changes their sign. So representation generated by XYZ, representation in which basis is XYZ, their character of I will be -1, so they belongs to U representation. Okay, whereas xy, xz, yz, x square, y square, z square, that is the linear the combinations of x, y, z will be +1 because -1 into -1 become plus. Here also -1 into -1 plus -1 square is equal to plus. Therefore, they become positive. That is character of I is equal to +1 for the symmetries whose bases are the combinations of x, y, z, that is xy, xz, yz, x square, y square, z square, and symmetry or the representation, irreducible representation having the basis xy, xz, yz have the character of I become +1, so they are G representation. They are G representation. That is A1G, B2G, like that. For example, if you consider, look at this character table. This is a character table for D4H point group. D4H. D4H is for the square planar molecule. Square planar molecules are centrosymmetric molecule. There is a center of inversion. Look here. There is a center of inversion. Okay. Then look at the representations formed by the x by z coordinate. Yes, z coordinate. Yes, here right to u. U is here because character of I is equal to minus 1 here. Very simple. Character of I is equal to minus 1, therefore it is u. And x by z, character of I is equal to minus. It is a two-dimensional representation, therefore minus 2. Okay, so character of, sorry, representation is u. U is here because character of I is equal to minus. Okay, clear. And in the case of the binary combinations, that is x square plus y square or z square, the character of I is equal to plus 1, therefore it is G representation. Okay, and x square minus y square, again, character of I is equal to plus 1, again G. xz, yz, character of I is equal to plus here, therefore EG. Okay, clear. That is, in the case of centrosymmetric molecule, the center of inversion I has minus sign in the case of x by z coordinate. Therefore, they belongs to U representation. And the character, sorry, okay, the representation belongs to the combinations of x by z. That is x square plus y square, z square, x y, x z, y z like that. The character of I is plus. Therefore, they belongs to G representation. And we know that only those modes are IR active in which they belongs to x by z coordinate. Okay, and only those mode belongs to the combinations of x by z, that is x square y square, z square, x y, x z, y z like that, are Raman active. Then you can see here very simply, very easily you can understand that only these vibrations, sorry, only the vibration which are IR active. These vibrations are IR active because they belongs to x by z coordinate. They cannot be Raman active because they are complementary because character of x by z is minus 1 but the character of these binary combinations are plus 1. So they never match each other. Okay, so IR active vibrations cannot be Raman active, and these are Raman active vibration which cannot be IR active because this xz, yz, x square, y square, etc. cannot be same as that of x by z. X by z cannot come here because x by z character of I is minus 1, x square, y square, z square, etc. character is plus 1. So they cannot match each other. Therefore, so they are complementary. Okay, so Raman active, IR active, this vibration, that is x by z coordinate are IR active. The x square, y square, z square coordinate are Raman active. So they are complementary. That is Raman active vibrations cannot be IR active and IR active vibration cannot be Raman active. Okay, this is our conclusion. That is for center of symmetric molecule, only the modes belongs to U representation can be IR active. Okay, why? Because U representation come have symmetry of x by z or their basis will be x by z. Okay, U representation character of I is equal to minus 1 and that belongs to x by z. So they are IR active. IR active. And only those modes belongs to G representation are Raman active. Okay, because G representation comes under this binary combination xy, xz, yz like that. So this is mutual exclusion principle. That is, in center of symmetric molecules, no Raman active modes is also infrared active, and no IR active infrared active modes are also Raman active. This is mutual exclusion principle. That is, the vibrations which are Raman active cannot be IR active, and vibration which are IR active cannot be Raman active. This is very simply explained using the uh, group theory. For example, consider an example this molecule N2F2. It has a center of inversion because at this center, if you draw a line towards this fluorine, similar line can be drawn towards this fluorine also. So there is a center of inversion center of inversion I for this molecule. This is a center of symmetric molecule. And its point group is C2H. Okay. There are 4 atoms, therefore number of degrees of freedom, number of vibrational degrees of freedom or internal degrees of freedom will be 3 into 3n minus 6, that is 3 into 4, 12 minus 6 is equal to 6. Okay, now we are fixing 12 Cartesian vectors on all the four atoms. We are fixing 3 coordinates. So there are 12 Cartesian vectors, and following reducible total representation can be generated. I will not explain more details. You will get this type, that is gamma is equal to 12 for E, 0 for C2, for I, this is small I, 0, and sigma is 4. Okay, on reduction, that representation of reduction, we get the irreducible, a combination of irreducible representation, that is total representation. This is gamma total 4Ag, 2Bg, 2Au, 4Bu. Okay, and from the character table of C2H, look at here, character table of C2H, gamma translation is here, Z is here, Au, X and Y here, that is Bu. Okay, Au plus Bu, that is the gamma translation. And gamma vibration, gamma, gamma rotation. Gamma rotation is Rz, Rx, Ry, that is Ag, Bg, Ag plus Bg. On subtracting Au, that is 2 Au is here, subtracting 1 Au, and Bu, 4 Bu is 1 Bu is subtracted, therefore we get 3 Bu. Okay, and Ag plus Bg, 1 Ag and 1 Bg is subtracted. Therefore, the gamma vibration is equal to 3 Ag, 3 Ag, 1 Ag subtracted from here, and 2 Bg is here. Therefore, on subtracting 1 Bg, okay, we get 1 Bg will be here, 1 Bg. Okay, and 2 Au, 1 Au is subtracted, therefore Au, and from 4 Bu, 1 Bu is subtracted, therefore it is 3 Bu. It is 3 Bu. Okay, and from this we can easily say that IR active vibrations, which are IR active? IR active vibration belongs to the symmetry of X by Z. Therefore, AU and BU are IR active. AU and BU are IR active. In C2H, AU and BU are IR active because IR active vibration are belongs to X by Z coordinate. X by Z coordinate. Therefore, AU and BU are IR active. And which vibrations are Raman active? Raman active vibrations are belongs to this binary products x square, y square, z square, xy, xz. Therefore, AG and BG are Raman active. Therefore, AG, and I think BG also will be here. BG is Raman active. There is no IR active vibrations are Raman active, and no Raman active vibrations are IR active. That is our conclusion, and it is called the mutual exclusion principle. This can very well and very easily, we can easily understand using the principles of group theory. Okay, thank you.